In section 8.3, we tested claims about a population proportion, and in section 8.4, we're going to test claims about a population mean. The requirements are the same as they were for test about a proportion. The sample has to be a simple random sample, and either or both of these two conditions has to be satisfied. You either have to be told that the population is normally distributed, or you have to have a sample size greater than 30. On the examples that follow, assume those two conditions are met, and let's talk about testing a claim about a population mean. In section 7.3, when we were making confidence intervals for population means, we said that if we were estimating the population mean, we probably didn't know the population standard deviation either. So rather than using a normal distribution, we used a t-distribution. In section 8.4, similarly, we're going to use a t-test when we don't know the population standard deviation, and that's the case in all of the following examples. We're going to use the same steps that we did in section 8.3. We're going to assume that a simple random sample has been selected from a normally distributed population. That means sample size doesn't matter. And test the given claim using a t-test. Identify the null hypothesis, the alternative hypothesis, the test statistic, the p-value, the conclusion about the null hypothesis, and the final conclusion that addresses the original claim. All right, example 1. In an analysis investigating the usefulness of pennies, the cents portions of 100 randomly selected credit card charges are recorded. The sample has a mean of 47.6 cents and a standard deviation of 33.5 cents. If the amounts from 0 to 99 cents are all equally likely, the mean is expected to be 49.5 cents. In other words, we're testing the usefulness of pennies, and that's been debated for a long time whether or not we should just do away with pennies. So this study is taking the cents portions of 100 credit card charges, and if pennies are really not worth anything or not worth keeping anyway, then you would have about as many charges above 50 cents as you have below 50 cents. If you find the expected value of 100 credit card charges, the cents portions, it would be 49.5 cents. If that mean is 49.5 cents, then we can do away with pennies. You have just about the same amount of charges above 49.5 cents as you have below 49.5 cents. And so if we did away with pennies, neither the consumer nor the business would lose money. Use a zero point zero 0.01 significance level to test the claim that the sample is from a population with a mean equal to 49.5 cents. What does the result suggest about the cent portions of credit card charges? We need to look for our key words here that tell us what to do on this problem. We're testing a claim, and the only two claims we have known how to test are claims about proportions and claims about means. So which one is this? This claim is that the sample is from a population with a mean equal to 49.5 cents. So this is a test about a mean, not a proportion. Test about proportions. We used one prop z-test, but in test about means, we're going to use t-test. Now that's in the same menu with one prop z-test on your calculator. If you press stat, move the cursor over to tests, t-test will be number 2. And like was the case for confidence intervals, if I have raw data, I'm going to highlight data, but if I have statistics about the data, then I'm going to highlight statistics. We'll have to decide that on each example. So the claim is that the population mean equals 49.5 cents. And remember what that means. If this claim is proven true, then doing away with pennies really wouldn't impact the economy. But that claim is false if the mean of the cents portions of these charges is not equal to 49.5. And the one of these two statements that does not have the equals to has to be the alternate hypothesis. That means the alternate hypothesis is mu is not equal to 49.5, and the null hypothesis always has equals in it. We had to be given a significance level, and we were. Use a 0.01 significance level. And then we need to extract the other values that we're going to enter on the calculator. Just like P sub 0 was the proportion stated in the claim in section 8.3, mu sub 0 is going to be the mean stated in the claim. So the mean stated in the claim is 49.5. The mean of our sample was 47.6, and the standard deviation of our sample was 33.5. So for the mean, I'm going to enter 47.6, standard deviation 33.5. The number of samples that we took, our sample size is 100. And then I need to let the calculator know whether I'm doing a left tail, right tail, or two-tail test. I need to indicate that by using the symbol in the alternate hypothesis. I'm going to make sure that I have mu is not equal to mu sub 0 highlighted on my calculator. On this example, I already have entered all of this information on the calculator, and I'll show you exactly what it looks like. I pulled up t-test under stat and test and number 2. I highlighted stats because I'm going to enter these statistics about my data rather than entering raw data itself. I entered the mean and the null hypothesis is 49.5. The sample mean is 47.6. The sample standard deviation is 33.5. Sample size is 100. And the symbol in my alternate hypothesis was not equal to. That lets the calculator know I'm doing a two-tail test. Move the cursor down to calculate and enter, and these are my results. If you need a moment to enter that data on your calculator, then just press pause and play again when you have all that information entered. Based on this results screen from my calculator, I got that the test statistic, I'm going to round it to 2 decimal places. My test statistic is t equals negative 0.57. And my p-value from the calculator rounded to 4 decimal places would be 0.5719. And I need to compare that p-value to the significance level I was given. My significance level is 0.01, and 0.5719 is much greater than 0.01. Since our p-value is greater than our significance level, what does that tell us about the null hypothesis? You may be thinking of it as if p is low, the null must go. You must reject the null hypothesis. If p is high, then we fail to reject the null hypothesis. And remember, fail to reject always means there's insufficient evidence of something. I just need to determine whether to say there's insufficient evidence to support the claim or there's insufficient evidence to reject the claim. I'm going to go ahead and put down there is not sufficient evidence . And then I need to think about my flow chart for determining whether to write there's not sufficient evidence to support or there's not sufficient evidence to reject. I'm referring to this flow chart, and hopefully you have it in mind by now. The first question is the alternative hypothesis the same as the claim? No, the alternate hypothesis was the complement of the claim. So they're not the same. And if they're not the same and I fail to reject the null, then I'm saying there's not sufficient evidence to reject the claim. And the claim that I'm rejecting is that the sample is from a population with a mean equal to 49.5 cents. And remember what that means. If the mean of my sample was 49.5 cents, that means doing away with pennies wouldn't significantly affect either the consumers or the providers. They're irrelevant in the economy and we should go ahead and get rid of them. But this sample, we didn't have enough evidence to reject that claim. We also didn't have enough evidence to support that claim. So we don't have enough evidence to do away with pennies at this time. One other thing about helping you with this final conclusion, if we had rejected the null hypothesis, if we had rejected the null, that would have meant we accepted the alternative. We would be saying this is true. And if this is true, then that would mean the claim is false. We would reject the claim. And that's why failing to reject the null means that there's not sufficient evidence to reject the claim rather than not sufficient enough evidence to support the claim. All right, example 2. The heights are measured for a simple random sample of 9 supermodels. Now, why is a sample size of 9 sufficient for conducting this hypothesis test? We were told in the beginning to assume that all the populations were normally distributed, and that's why we can use a sample size of 9. Our 9 supermodels had a mean height of 70 inches and a standard deviation of 1.5 inches. Use a 0.01 significance level to test the claim that supermodels have heights with a mean that is greater than the mean height of 63.6 inches for women in general. So perhaps this claim is being made by some disgruntled short person who's frustrated because she can't be a supermodel, and she's saying it's discrimination that you have to be taller than average in order to be a supermodel. Is there proof that you have to be taller than average to be a supermodel? Well, that's what the test is about. The claim is that the mean is greater than 63.6. The mean height of supermodels is greater than 63.6. And that's false if the mean is less than or equal to 63.6. Remember, the equals has to be in one of these two statements. These two statements have to be the complements of each other. The alternate hypothesis is the one of these two that does not have the equals. So the alternate hypothesis is that the mean is greater than 63.6, and the null hypothesis is that the mean equals 63.6. We're told to use a 0.01 significance level. And on the calculator, I'm going to enter the mean in the null hypothesis is 63.6. The mean of my sample is 70, and the standard deviation of my sample is 1.5. My sample size is 9, and the symbol in the alternate hypothesis is greater than. So I have to tell the calculator I'm conducting a one-tail, specifically a right tail test. All right, I'm ready to enter that information on the calculator. I'm going to pull up test and or stat and then test, and then number 2 is t-test. Once again, I'm given statistics about the data. I'm not given the raw data itself. I'm going to enter that the mean in the null hypothesis is 63.6. The mean height of my supermodels was 70 inches with a standard deviation of 1.5 inches. That was for 9 supermodels, and I am conducting a right tail test. So move the cursor down to calculate and enter. Here's my alternate hypothesis. Mu is greater than 63.6. My test statistic is t equals 12.8. And think about that. That's like a z-score. That's a number of standard deviations from the mean. How likely is it that if you don't have to be taller than average to be a supermodel, how likely is it that we would have gotten a sample that was almost 13 standard deviations from the mean? 13 standard deviations from the mean is unheard of. 99.7% of all values lie within 3 standard deviations of the mean, and this is 13 standard deviations from the mean. So I'm expecting a very, very small p-value. And be careful not to say the p-value is 6.5455 because that doesn't even make sense for a probability. Your probability has to be between 0 and 1. So you notice from looking at the calculator that this is in scientific notation. Move the decimal 7 places to the left and then round it to 4 decimal places. There's practically no chance that this sample would have had a mean that was 13 standard deviations from the population mean. Excuse me. That p-value is less than almost any significance level that I could have used. And since my p-value is less than alpha, what do you say about the null hypothesis when p is low? When p is low, you reject the null hypothesis. And that means there is sufficient evidence for something. We just need to know whether there is sufficient evidence to support the claim or sufficient evidence to reject the claim. We rejected the null hypothesis. That means we're accepting that the alternate hypothesis is true. That means we're saying that the mean height of supermodels is greater than the height of the average woman, and that's what the claim was. These are the same. So if I have proven this, I have supported my claim. There is sufficient evidence to support the claim that the mean height of supermodels is greater than the mean height of women in general. If a disgruntled short person brought this claim to court, then she has proven that you do have to be taller than average to be a supermodel. Is she likely to be awarded any damages in court if she was suing because she wasn't accepted as a supermodel because she was short? The answer is no. There's no law against height discrimination. There are laws against age discrimination and gender discrimination and racial discrimination and other types of discrimination, but you can't sue because you were too short for a job or you were turned down for a job based on your height. So she has proven her claim that you do have to be taller than average to be a supermodel, but yet there's no law against that. All right, I have two more examples. And in these two examples, I'm given raw data rather than statistics about my data. That means when I pull up t-test, I'm going to have to highlight data instead of stats, and I need to already have this data in my list on the calculator. A simple random sample of pages from Merriam-Webster's Collegiate Dictionary is obtained. The number of words defined on the pages are as follows, and I gave you 4, 8, 9, 10 words on the pages that were in the random sample. Given that the dictionary has 1,459 pages with defined words, the claim that there are more than 70,000 defined words is the same as the claim that the mean number of defined words on a page is greater than 48. Now let me think about where that 48 came from. If the dictionary had 70,000 words in it, as it claims, defined words, and we divided that by 1,459 pages in the dictionary, that's the 48 words per page. If the dictionary does have 48 words per page for the 1,459 pages, then yes, it does have about 70,000 defined words in it. Use a 0.05 significance level to test the claim. That means we're doing a hypothesis test. And the claim is about the mean. That means we use t-test rather than one prop z-test. And the claim is that the mean is greater than 48. The claim is that mu is greater than 48. And that's false if mu is less than or equal to 48. And the one of these two statements that does not have the equals is my alternate hypothesis. The claim doesn't have the equals, so it's my my alternate hypothesis. And the null hypothesis always has equals. I was told to use a 0.05 significance level. And I don't have all of these statistics to enter on the calculator. I have this raw data. I can still say that the mean in the null hypothesis is 48, but I don't know X bar and S. I'm going to let the calculator calculate those for me. I can tell you that I had, 10 values in my sample. And this is a right tail test because the alternate hypothesis had a greater than in it. But since I'm not given this information, I need to enter these values in a list on my calculator and then choose data when I pull up t-test. All right, it looks like I do have 10 values entered. I'm going to scroll back up to the top and double check them. 51, 63, 36, 43, 34, 62, 73. 39, 53, 79. So I have all that data entered correctly. I want to exit the stat editor and then pull up t-test. And I need to tell the calculator that I want to run a t-test on data that I've put in list one. The mean and the null hypothesis is 48. I've put my data in list one. If you put your data anywhere else, make sure you change that. Leave frequency equal 1, and then tell the calculator the symbol in your alternate hypothesis is greater than, so you want a p-value for a two-tail test. And then scroll down to calculate, and there are your results. Your p-value, rounded to 4 decimal places, is 0.1561. And your test statistic is that t-value 1.07. Since my p-value is greater than the significance level, that's all I need to formulate my initial conclusion. And since my p-value is greater than alpha, that means I failed to reject the null hypothesis. And if I failed to reject the null hypothesis, then my conclusion is going to begin, there is not sufficient evidence for something. My claim is the same as my alternate hypothesis. So if this was true, I would have proven my claim. There's not enough evidence to say this is true, so there's not enough evidence to support my claim. And I could say that the claim is that the mean words per page is greater than 48. Since we're really talking about whether or not there are more than 70,000 words in the dictionary, I'm going to say there's not sufficient evidence to support the claim that there are more than 70,000 defined words in this dictionary. If I had rejected the null and accepted the alternate, then I would have supported my claim. But since I couldn't reject the null, I have to say there's not enough evidence to support my claim. All right, let's do one more. Cans of paint usually advertise how much area 1 gallon of paint will cover. Super Paint claims that 1 gallon of its paint will cover 400 square feet. To test this hypothesis, 10 gallons of paint were tested, and the actual area covered by each can is as follows. I'm going to go ahead and enter those 10 square footage amounts in my stat editor. 310, 315, 415, 365, 445, 375, 300, 410, 365, and 350. All right, go back and double check that data. I don't want to miss the whole problem because I made a typo in entering data. My areas are 310, 315, 415, 365, 445, 375, 300, 410, 365, and 350. That's correct, so I can quit my stat editor. All right, what's the claim here? The claim is that, does the data indicate? Let's see. The company's claim is that a gallon of paint will cover 400 square feet. So the company's claim is that the mean is 400. And that's false if the mean is not 400. So the alternate hypothesis has to be the not 400, and the mean, the null hypothesis, has to have an equals in it. I'm asked to use a 0.05 significance level. The mean in the null hypothesis is the 400. I'm not going to enter the sample mean and the sample standard deviation because I'm going to use my raw data instead. My sample size was 10 gallons of paint, and I want to conduct a two-tailed test because the alternate hypothesis has a not equals in it. So I'm going to pull up t-test and say I'm entering data once again, where the claimed mean is 400 square feet of area. I've saved my data in list 1. I'm going to leave that frequency 1 for all the tests, and make sure you change your symbol in the null hypothesis to not equal to. You actually have to enter to make the calculator choose not equal to mu sub 0. And then calculate and enter again. For a test statistic to 2 decimal places, I got t equals negative 2.29. And for my p-value, I got 0.0477. If I'm using a 5% significance level, then that's less than my 5% significance level. And since p is less than alpha, what does that mean? That means I can reject my null hypothesis. Notice if we had used a lower significance level, if this had said test at a 0.01 significance level, then I would fail to reject the null hypothesis. So rejecting or failing to reject depends on that significance level that's used. When I reject the null hypothesis, I accept the alternate hypothesis, and that means that I'm saying the mean is not 400. The company claimed that the mean is 400. I just proved that the mean is not 400. So there is sufficient evidence for something. Is it to support the claim or to reject the claim? Again, I've proven that the mean is something other than 400. The company claimed that the mean is 400. So I have just disproven or rejected their claim. I've rejected the claim that the mean area covered by a gallon of super paint. I've rejected the claim that the mean area is 400 square feet. I'm not saying whether it's more than 400 or less than 400. That's not part of my test. I just proved that the mean area is not 400. It's something else. So they need to change their claim. All right, you should be ready to do the next My Stat Lab or My Labs Plus assignment. Don't forget that in Momentum, I have posted two worksheets, one for hypothesis testing claims about proportions and the other with hypothesis testing claims about the mean. This worksheet basically, I've just given you these 7 steps so that you can fill in the blank. That would be very helpful to you in organizing your information so that you enter it correctly on the calculator. Have a good day.